Here we're going to derive an amazing trigonometric identity due to Ramanujan. So the goal is to put these three terms together into one object. So we have the cube root of 2 cosine pi over 9 minus the cube root of 2 cosine 2 pi over 9 minus the cube root of 2 cosine 4 pi over 9. And we'll be able to put this together into the cube root of one thing. And we'll do that with this theorem, which is also due to Ramanujan, that says the following. So if we let alpha, beta, and gamma be roots of this cubic polynomial, x cubed minus ax squared plus bx minus 1 equals 0, then the cube root of alpha plus the cube root of beta plus the cube root of gamma equals the cube root of a plus 6 plus 3t, where t is defined by this cubic polynomial. So we have t cubed minus 3 times the quantity a plus b plus 3t minus the quantity ab plus 6a plus b plus 9 equals 0. So it's kind of a mouthful. So our goal is to prove this theorem and then find a polynomial that has these guys as roots and then apply this theorem to this polynomial. Okay, so let's get to the proof of this theorem. The first thing that I want to notice for the proof is that x cubed minus ax squared plus bx minus 1 is the same thing as x minus alpha, x minus beta, x minus gamma. But then if we were to multiply it out, we could definitely get a handle on all of the coefficients of x cubed, x squared, x, and 1, but those aren't really helpful at the moment. So we'll just notice that if we were to multiply this out, we'd get x squared plus a bunch of stuff and then minus alpha, beta, gamma. But now equating the constant terms on both sides of this equation shows us that minus 1 equals minus alpha, beta, gamma, which is the same thing as saying alpha, beta, gamma equals 1. Great, so that's actually going to be extremely helpful. And in fact, we can also say that the cube root of alpha, beta, gamma, which is the same thing as the cube root of alpha times the cube root of beta times the cube root of gamma also equals 1. Okay, fantastic. So the next thing that we want to do is define two new numbers, theta and phi, by the following expansion. So we'll take z minus the cube root of alpha times z minus the cube root of beta times z minus the cube root of gamma. So notice that's going to multiply out to something kind of similar to this, except we'll have different coefficients, and we'll name those coefficients. So here we'll have z cubed minus theta z squared plus phi of z, and then minus 1. And again, we know that this is minus 1 because that coefficient is negative cube root of alpha times cube root of beta times cube root of gamma. But then taking this polynomial and finding the roots of this polynomial, in other words, setting equal to 0 and then finding a solution to this, is equivalent to finding a solution to the following equation: z cubed minus 1 equals theta z squared minus phi of z. And then just to reiterate, the solutions to this equation are z equals cube root of alpha, cube root of beta, and cube root of gamma. And that's because we've got this factorization above. That was our definition. Now if we cube both sides of this equation, we'll create a new equation that also has these solutions. It'll have some additional solutions, but it'll at least have these solutions. So let's go ahead and cube both sides of this equation to see what we get. Great. So notice I'm just going to write this thing as z cubed minus 1 cubed, and now I'm going to go ahead and multiply this one out. So that's going to give me theta cubed z to the 6th, and then minus 3 theta squared phi z to the 5th, and then plus 3 theta phi squared z to the 4th, and then finally minus phi cubed z cubed. Okay, great. So that's what I get from multiplying out that right-hand side. Okay, now the next thing that I want to do is put some of these terms on the right-hand side together. In fact, I want to rewrite this as theta cubed z to the 6th minus phi cubed z to the 3rd. And then I want to take this and factor some stuff out. So just to reiterate, I'm going to take these two terms and factor something out of it. So from this blue part, I'm going to take out a minus 3 theta phi z cubed, and let's see what that leaves me with. So that's going to leave me with a theta z squared in this term, and then in this term, I'm going to get a minus phi times z. Okay, so that's looking good. But now, let's notice from up here, before we cubed this, we know that theta z squared minus phi z is equal to z cubed minus 1. So I can just replace this with z cubed minus 1. And now we can move this all around and see what we have. So we're going to have z cubed minus 1 cubed, and then we'll have minus theta cubed z to the 6th plus phi cubed z cubed, and then minus 3 theta phi z cubed times z cubed minus 1. And so that's equal to 0. So that is equivalent to this equation up here. So let's just reiterate. This equation right here is equivalent to this equation right here. Okay, so I'm going to go ahead and move this equation up, keep everything that I need, and then we'll go on to the next step. On the last board, we defined this theta and phi by the expansion of this z minus the cube root of alpha, and so on and so forth. Then, doing some manipulation on this equation, we found a new equation which is a 9th degree polynomial for which the cube root of alpha, the cube root of beta, and the cube root of gamma are roots of. And it is this equation right here. Now, the next thing that I want to observe is that this is actually a cubic polynomial in a change of variable u equals z cubed. So let's go ahead and see what we get if we exchange all of the z cubes for u's here. So let's look at that real quick. Okay, so this gives us this cubic polynomial in the variable u. So we have u minus 1 quantity cubed minus theta cubed u squared plus phi cubed u minus 3 theta phi u times u minus 1. Great. And then the next thing that we want to notice is that we know some of the roots of this. So again, the roots are when z is equal to the cube root of alpha, the cube root of beta, and the cube root of gamma. But then by this equation right here, we see that the cube root of u is equal to z. So that gives us the roots of this in terms of u values. So the roots of this are u equals alpha, beta, gamma. Okay, great. Now the next thing that we want to do is multiply this thing out. So let's see what we get when we do that. So now multiplying this out, we get this cubic polynomial, which is the same as this one, just everything multiplied out. But recall, the roots of this are still alpha and beta and gamma. But the roots of our original equation were also alpha, beta, and gamma. So what that tells us is we know something about these theta and phi values. We know that this one equals a, and we know that this one equals b. So in other words, we have a equals theta cubed minus 3 theta phi plus 3, and we have b equals phi cubed minus 3 theta phi plus 3. But now notice that that allows us to solve this for theta cubed and phi cubed. And in fact, this is going to give us theta cubed equals a plus 3 theta phi minus 3. And then similarly, phi cubed is equal to b plus 3 theta phi minus 3. So what I'll do now is I'll bring that to the top and we'll move on to the next step. So we're still working with our theta phi values, which were defined by the expansion of this polynomial. That gave us formulas for theta cubed and phi cubed in terms of a, b, and theta times phi. Now the next thing we want to do is introduce a new value, and that will be t. So t is going to be equal to theta times phi minus 3. And so now flipping that a little bit, we see that theta times phi is equal to t plus 3. Great, and now we're going to inject this into each of these. That's going to give us theta cubed equals a plus 3 times t plus 3 minus 3, which is going to be equal to a plus 3t plus 6, because we've got plus 9 minus 3. And notice that's getting to look like this thing over here, which was kind of our goal. And then furthermore, if we take phi cubed, we're going to have b plus 3 times t plus 3 minus 3, which is b plus 3t plus 6. So now we have these nice values for theta cubed and phi cubed in terms of our new object t and our old coefficients a and b like we had over here. So the next thing that we want to do is take this polynomial and expand it out 2 ways. So let's just go ahead and copy this down now. So we've got z minus cube root of alpha times z minus cube root of beta times z minus cube root of gamma. Great. So then by definition of theta and phi, that's equal to z cubed minus theta z squared plus phi of z minus 1. Great. And then by just multiplying that out really carefully, notice we're going to get z squared and then minus the cube root of alpha plus the cube root of beta plus the cube root of gamma times z squared, and then plus the cube root of alpha beta plus the cube root of beta gamma plus the cube root of alpha gamma minus 1. Okay, fantastic. But now we can equate these coefficients, and notice that we've got this cube root of alpha plus cube root of gamma plus cube root of beta equal to theta. Great. And then also we have this thing, which is the cube root of alpha beta, and then the cube root of beta gamma, and then the cube root of alpha gamma is going to be equal to phi. Okay, good. So now what's really important now is this equation, and then the equality of this pink circle, and this blue circle, and that blue circle. So what I'll do is I'll erase everything else, and then I'll bring that up, and we'll work from there. So far we've constructed the following equations. So we know theta cubed is a plus 6 plus 3t, phi cubed is b plus 6 plus 3t, and recall that phi and theta were related to t by t plus 3 equals theta times phi. And then finally, by expanding a certain polynomial 2 different ways, we got the cube root of alpha plus the cube root of beta plus the cube root of gamma equals theta, and then the cube root of alpha beta plus the cube root of beta gamma plus the cube root of alpha gamma is equal to phi. Now we want to use these 2 facts to write theta and phi in terms of t and a and b. So here notice that theta is equal to the cube root of theta cubed, so that's going to make this thing equal to the cube root of a plus 6 plus 3t. And notice that's exactly the result that we were looking for. And notice we get this bonus result by doing the same thing with phi. So we have this sum of cube roots over here on the left-hand side is equal to the cube root of b plus 6 plus 3t. Now we won't use this one for our final goal. We'll only use this one, but it's nice to see this as well. But we're not quite done. We do have this relationship between these sums of these cubes involving the roots of our original polynomial and these kind of things over here, but we have not yet shown that our t value satisfies this equation down here, and so that's what we need to do. So we'll pick up from this definition. We have t plus 3 equals theta times phi, and notice that tells us that t plus 3 cubed is equal to theta cubed times phi cubed. But we have nice expressions for theta cubed and phi cubed. That's equal to a plus 6 plus 3t, and then b plus 6 plus 3t. Now the next thing that I want to do is multiply out both sides of this equation. So that's going to give me t cubed plus 9t squared. So notice I get a 3 from the binomial coefficient and then a 3 from this right here, plus 27t. Again, I get a 3 from the binomial coefficient and then times 3 squared. And then finally plus 27, and that is from 3 cubed. So that's what happens to this left-hand side. Great, and now we need to multiply that out that right-hand side. So let's see what we get here. We get AB plus 6a plus 3at plus 6b plus 36 plus 18t. So that's what we get from multiplying these first two terms onto that last guy. And then finally we have plus 3bt plus 18t plus 9t squared. So now let's see what we can do here. Notice that this 9t squared is going to cancel this 9t squared. And then we can also combine some things on the right-hand side. So this 18t and this 18t will combine together to give us a 36t. So we're adding on a 36t after scrubbing those off. And then let's see what else we have. So those are all the like terms. Great, so now let's rewrite this real quick. So we have t cubed plus 27t plus 27 equals, great. So now we want to move everything over here from the right-hand side to the left-hand side. And I'll let you check all the details. But after moving everything from the left-hand side to the right-hand side, we will achieve this polynomial over here. And that actually finishes the proof of this theorem. So let's go ahead and move on towards proving our final result. Okay, so this polynomial is going to seem like it came out of nowhere, but to be honest, it's just one that really works with an application for this theorem. So we're not going to say really where it came from, we're just going to notice that it will work with an application of this theorem. Now, in order to work through this and apply this theorem, we not only need to know a and b, which are actually quite simple. A is equal to 0 and b is equal to -3, but we also need this value t, and that's actually going to be a bit tricky to get. So let's notice down here by this definition, we have t satisfies this polynomial equation. Okay, so now plugging our a and our b values into this polynomial, we'll see that this part goes to 0 because we have a plus b plus 3, but that's 0 plus -3 plus +3, so that's going to leave us with t cubed minus, and now let's see what we get for that. So notice that a times b is 0, and then a plus b is -3, so that's going to give us 6 times -3, and then plus 9, so that's equal to 0. Great. So the next thing to notice is that this is going to be equal to -18 minus 9, so that's -9. So that gives us this t cubed plus 9 equals 0. In other words, t equals negative the cube root of 9. Okay, good. And why is it not one of the imaginary roots? It is not one of the imaginary roots because notice everything over here is going to be a real number, so we're okay. So let's go ahead and add that up here. So this is something that we no longer need. We have it. So t is negative the cube root of 9. Okay, great. So we don't need it. We have it. Okay, great. So I'm going to clean this little bit up, and then we're going to find the solution to this polynomial equation. Now we're going to go ahead and find a solution to this polynomial equation, and we're going to use a substitution trick in order to work towards a solution. Let's go ahead and let x equal t plus 1 over t, and let's see what that does to this equation. So notice here we're going to have t plus 1 over t cubed minus 3 times t plus 1 over t minus 1 equals 0. Okay, so let's simplify this a bit and see what we get. So notice this is going to be t cubed plus 3 times t squared times 1 over t, so that's going to be 3t, plus 3 times t times 1 over t squared, so that's going to be 3 over t, and then plus 1 over t cubed. So that's what we get from multiplying this out. Notice I just used the binomial theorem real quick. I know the binomial coefficients. And then next here we have, this is minus 3t minus 3 over t minus 1 equals 0. Okay, so some stuff is obviously going to cancel. Notice that this guy cancels with this guy, and this guy cancels with this guy. And we're left with t cubed plus 1 over t cubed minus 1 equals 0. Okay, so the next thing I want to notice is that t equals 0 is not going to give me a solution because notice that is 0 in the denominator. So I'm going to go ahead and multiply this whole thing by t cubed to clear the denominators, and that's going to give me t to the 6th minus t cubed plus 1 equals 0. Okay. Now, the next thing I want to do is make this a little bit more friendly, and I'll do that by multiplying this whole thing by t cubed plus 1. So now notice if I multiply this out, a lot of stuff is going to cancel, so I won't do all the details, but here what I get is t to the 9th plus 1 equals 0. So let's go ahead and bring that up, and we almost have a solution. All right, let's see where we were on solving this polynomial equation. We made the substitution x equals t plus 1 over t. That gave us the equation t to the 9th plus 1 equals 0 after putting it in here and letting everything cancel. That's the same thing as t to the 9th equals negative 1. But something subtle happened, and along the way we multiplied by t cubed plus 1, which means t cubed plus 1 here is not allowed to be 0 because that was not an original part of the solution. In other words, t cubed cannot be negative 1. So that means we want to solve this equation right here, t to the 9th equals negative 1, but then disregard the solutions t cubed equal negative 1. Okay, so let's go ahead and do that. So I'm going to use complex numbers to do this. So I have t to the 9th. So I'm going to write negative 1 as e to the I pi, but then I need 3 solutions because I want to find all roots of this polynomial. So what I'm going to do here is add on a multiple of 2 pi ki. So in other words, I've got something like this, e to the I pi, and then 1 plus 2k. Great. And now this is actually going to be true for all k integers. Okay, so why is that the case? Well, it's because when you expand this in terms of sines and cosines, which we will do eventually, those have a period of 2 pi, so here we're just kind of going all the way around the circle. So now we're going to go ahead and take the 9th root of both sides, and that's going to give us t equals e to the I pi, and then we have 1 plus 2k over 9. And here we're going to have 9 solutions to this equation. We'll have to throw all but 3 away, but let's get those 9 solutions first. And those solutions are going to be for k values 0, 1, 2, all the way up to 8. Because if we hit k equals 9, then we've looped all the way around the circle because we're dividing by 9 here. So notice, plugging these numbers in, we're just going to get consecutive odd numbers in the numerator here. So let's see, here we'll have e to the I pi over 9. That's what we get for k equals 0. And then we have e to the I 3 pi over 9, which is the same thing as pi over 3. E to the I 5 pi over 9. E to the I 7 pi over 9. E to the I 9 pi over 9, which is just e to the pi I, which is negative 1. Okay? And then e to the I 11 pi over 9, and then e to the I 13 pi over 9, and then e to the I 15 pi over 9, which is the same thing as 5 pi over 3, and then finally e to the I 17 pi over 9. Okay, great. And those are all the different ones. So now let's see which ones we need to throw out. So we'll need to throw all of them out that are solutions to that equation. So notice that this guy is the solution to that equation, negative 1. But then this one is as well, because if we cube this, we get e to the I pi, which is negative 1. And then this one is as well, because if we cube this, we get e to the I 5 pi, which is also negative 1. Okay, so we've got 6 left, but we're actually done paring down because notice that these come in inverse pairs. So notice e to the I pi over 9 and e to the I 17 pi over 9 are inverse pairs. E to the I 5 pi over 9 and e to the I 13 pi over 9 are inverse pairs. And then finally e to the I 7 pi over 9 and e to the I 11 pi over 9 are inverse pairs. And then that may not matter if we're just looking at this equation, but since we're looking at this equation up here in terms of x that use this change of variables x equals t plus 1 over t, then we only need to keep one guy from each inverse pair. So we'll go ahead and keep this one, and then this one, and then finally this one. These will be the 3 that you keep. Because those over there are superfluous, they will give us the same result. Okay, so let's go ahead and bring this up and then we're almost done. Okay, we've got our 3 important solutions for our t equation, and now before we turn those into x numbers, I want to do one more thing, and that is I want to notice that if t equals e to the I theta, then that means x equals e to the I theta plus e to the minus I theta. But that simplifies nicely using Euler's formula. Notice that this is cosine theta plus I sine theta, and then plus cosine theta minus I sine theta, which gives us 2 cosine theta. Great. But now applying that to each of these one at a time, we'll get these are our 3 roots. So our first root will be x equals 2 cosine pi over 9. Our second root will be x equals 2 cosine 5 pi over 9. And then finally our third root will be x equals 2 cosine 7 pi over 9. Great. Now the next thing that I want to do, in order to make these guys look like these numbers up here, I want to apply some sort of trig identity. So notice that this equals 2 cosine, and then 5 pi over 9 is the same thing as pi minus 4 pi over 9. But then there's a trig identity that allows us to write that as negative 2 cosine 4 pi over 9. Great. And then similarly, we can write this as 2 cosine pi minus 2 pi over 9, but that's going to be equal to minus 2 cosine 2 pi over 9. Okay, great. So what that tells us is that the roots of this equation are these 3 values down here. Okay, so now I'll clean up the board and then we'll put it all together. Okay, we've been working with this polynomial. We finally got the roots for alpha, beta, and gamma. 2 cosine pi over 9, minus 2 cosine 2 pi over 9, and minus 2 cosine 4 pi over 9, where in the language of this theorem, we had an a value of 0, a b value of minus 3, and a t value of minus cube root of 9. So now let's put all of those together. We know that this is like the cube root of alpha plus the cube root of beta plus the cube root of gamma. And now applying this, we should get the cube root of a plus 6 plus 3t, but notice that's going to be 6 minus 3 times the cube root of 9. So we're able to put all of these cube root of cosine type things into this one nested radical. Great, and that's a good place to stop.